Welcome. In this session, we will analyze the economic and architectural factors that cause AI networking costs to grow disproportionately as you scale your infrastructure. To understand the cost, we must first understand the workload. Traditional data center apps are loosely coupled, meaning they scale linearly at a server, get more capacity. AI training is different. It is a distributed computing problem where hundreds of GPUs act as a single computer. Because of this tight coupling, the entire job runs only as fast as the slowest link, a concept known as tail latency. This forces us to build lossless, non-blocking networks. Cannot rely on statistical sharing of bandwidth like we do with web traffic. Instead, we must provision enough capacity for every GPU to talk to every other GPU simultaneously, which sets a high baseline for infrastructure costs. This flowchart distinguishes the workload types. We start with AI workload characteristics. The critical divergence is at coupling type. While loosely coupled apps allow for cheap standard oversubscription, AI's tightly coupled nature means all nodes sync. This leads to tail latency determining the speed, ultimately forcing the adoption of a high-cost non-blocking fabric to ensure expensive GPUs aren't waiting on the network. As we scale the physical topology, cost compound, we use a fat tree architecture to maintain high bandwidth. For a single scalable unit or SU, we only need leaf and spine switches. However, as we connect multiple SUs into a super POD, we must introduce a third layer, the core group. This isn't just adding more cables, it's architecting a massive central switching complex. For example, 140-node Super POD organizes switches into spine groups and core groups to ensure non-blocking performance. Every time you add a layer to the topology to support more nodes, you are buying significantly more infrastructure just to keep the existing nodes connected at full speed. Here we visualize the topological jump. On the left, a single SU requires only leaf and spine switches. On the right, scaling to a Super POD forces the insertion of core switches above the spine groups. This new top layer, highlighted in orange, represents the nonlinear jump in infrastructure required to interconnect the units without sacrificing bandwidth. Look at the hard numbers to see the multiplier effect. For a small 20-node system, you might need about 13 switches. That's roughly 65 switches per node. But if you scale to a 140-node Super POD, you need 164 switches jumping to 17 switches per node. The infrastructure burden per unit has nearly doubled. Furthermore, this requires over 300 cables when factoring in storage and management fabrics. We aren't just buying servers, we are building a massive optical plant. The cost of high-speed transceivers for thousands of links often rivals the cost of the switching hardware itself, driving the nonlinear cost curve. This bar chart quantifies the hardware multiplier. The x-axis compares a 20-node cluster to a 140-node cluster. Y-axis shows the switches per node ratio. Notice the jump from 65 to 17. This visualizes how the networking overhead per server increases as the total system size grows, mathematically proving the nonlinear cost scaling. Finally, we must account for operational expenses, OpEx. Those 164 switches in a Super POD generate significant heat, driving up power and cooling costs nonlinearly. Beyond utilities, the complexity of managing thousands of optical links creates a new challenge. You cannot manually debug this scale. Need advanced telemetry platforms like NVIDIA UFM Cyber AI to detect anomalies and predict failures before they ruin a month-long training run. Additionally, to ensure resilience, we deploy redundant configurations like dual-rail hosts. This operational complexity requiring specialized software, power, and human expertise adds the final layer to our nonlinear cost model. This mind map breaks down the operational expense drivers. The central OpEx drivers node, we branch into complexity, requiring tools like UFM telemetry. We branch into resilience, necessitating investments in dual-rail hosts. Finally, we look at physical costs, where power consumption and advanced cooling demands rise sharply with the added switching infrastructure.